Okay, so today is a very important lecture on the canonical partition function and the canonical ensemble. Essentially, we're getting into the Helmholtz representation. I'd just like to mention that about this this number omega that I've been talking about in lecture 8, the first lecture on StatMech. I gave the example of a particle in a box, and if on these axes I would have, say, the x-coordinate of, let's say I have two particles in a box, so let's say, well, they may be distinct or they may be identical. I don't want to say anything more about identical particles here, quantum identical particles here, but I just want to mention that what this omega means is that if there are certain integers n like this, and remember what the energy was, it depended on, you wanted the sum of the squares of this and this to be equal to a certain number, or to be within a certain range. Maybe, if the accessible region is this, then there are integer points in here, a certain number of them. I won't draw them all, let's draw them like this. But there may be some missing ones, one here, one here. The reason they're missing can be all sorts of things. In quantum mechanics, if these two particles are identical, then there will be missing ones in here. Or if they may be missing for other reasons, simple reasons like the sum of the squares don't equal the energy. All kinds of reasons why there'd be missing states in here. So it's not quite true that the number of states is the same as the volume. The number of accessible states is the same as the volume in the state space. Okay, or in the classical description, I'd be talking about phase space. It's not quite true that it is equal to the volume. It's something that depends on the volume, but it's not exactly equal to it. And the exact relationship I don't want to get into right now. There's been quite a lot of controversy about it in the last 10 years, actually. Some people have been advocating changing a different definition of entropy, even based on probability rather than phase space volume. I don't want to get into that at all at the moment. But as long as you keep in mind that there can be holes in the gaps in the accessible states, then it's okay, because you'll realise that at some point you're going to have to be able to count the gaps, if you like, or account for the gaps. Okay. Otherwise, if you just have the entire volume, and if you say that each of these, if this is the semi-quantum picture, semi-classical picture. If each of these is a unit volume, and if you just say that the volume of this is equal to the number of states, then you're overcounting. Yeah. Anyway, that's something that I want to point out. Now, this is for a particular energy between E and E plus delta E, but there may be another. If it's somehow possible to supply the system with energy, and at the higher energy, there'd be other sets of possible states in the semi-classical picture, with its own holes. Maybe holes in completely different locations, could be anywhere. Or there may be some very regular reason which allows you to count them. What you already can appreciate is that the number of accessible states at the higher energy, even if it's just a fraction higher, would be very much larger than the number of accessible states in the lower energy states, because even with the simple example, you can see that with a single quantum particle. But maybe okay. What about the ensemble that would describe, for example, if the system is known to have an energy E to within some inaccuracy, then that's a microcanonical ensemble, is the appropriate ensemble for that. And we would expect that there will be no favour. The system would not favour any of the accessible states as long as they have energy in this band. And so they would, the energy, the distribution of systems in the ensemble would be equal among all the accessible states at this energy. If we had another microcanonical ensemble at this higher energy, then likewise we'll have an equal distribution of systems in the ensemble in only that energy. You know, if a microcanonical ensemble, if we knew that the system had this energy or in this band, then these would be equally likely. Okay. Maybe actually the probability distribution depends on the energy. Now remember, actually in lecture 9, I showed that the log of the ensemble, the probability that in the classical, and I gave a classical argument that the log of the ensemble, the probability, the distribution in the ensemble is some constant, is a linear combination of some constant plus
integral constant of motion.
What's it? This is a log. This is log. This is some constant plus what was it?
AE.
AE.
Yeah. Plus
AE. Yeah. That's the energy. This is a single energy of a single state.
Yeah, because this is a
single state. In fact, the probability distribution would be in general. You could have the physical realization of any of these could be different. So this one is constant. So this would be could be used for the microcanonical ensemble, where the probability is 0 outside the accessible region, or even where the gaps are, and equal everywhere in the accessible region. So that's constant. So that is the microcanonical ensemble. Microcanonical ensemble.
Could you repeat the interpretation of alpha?
Oh, this one is just. So there were 7. In three-dimensional space, there are 6 basic infinitesimal operations that you can perform on an appropriate Hamiltonian that would leave the Hamiltonian invariant. So there's translation in 3 directions and rotation around 3 axes. So that gives extra terms here. I can't remember alpha. This is actually beta. Gamma vector dot total momentum. That's the momentum of the center of mass. Gamma delta vector, and this was the angular momentum, total angular momentum of the system. We're not concerned in this course about these ones. If you're doing astrophysics, you'll see this one, and particularly you probably generalize it to the relativistic case. This one possibly as well, but we're only interested in the first 2, and so a constant is essentially independent of the other 7. Yeah. So that's why it's there. And so P equals constant, and another type of situation would be P equals e to the, turns out minus beta e. We want a negative sign there because classically the energy can be we'll define some 0 for the energy, and it can be from 0 to infinity. So we want a minus sign there, and this is a constant there. This is called the canonical ensemble. and it's easy to check that the probability distribution is constant in time in the accessible region. Whether it's that or that, they're both constant in time, they just don't change. So these are valid ensembles that can that can describe a thermodynamic system in equilibrium, so that all the average quantities remain constant. Okay.
What if we increase n, the number of particles there?
Exactly, that's a really good question. What about n? What about the number of particles? We haven't said anything about changing the number of particles yet. That's a really good question, but we'll get to that in future lectures. Yeah. In fact, this is kind of like a basic form, and from this you derive the n dependence. It's there are various arguments for that. In fact, that's one of the controversies at the moment. How do you actually do that? All right. But this is the most fundamental derivation of these two forms. And what we're going to do today is to derive this at a more concrete level by considering a system in contact with a heat reservoir.
Professor, do the anomalies in the state, the missing states, do they decrease when we increase the number of? Does it approach the volume? If we assume unit volume per accessible state, per state?
No, they'd be significant. They can be significant in classical statistical mechanics. They can be significant. The examples going around at the moment that have contradicted quite a lot of textbooks are in types of systems called colloids. Colloids are like, for example, globules of lipids, fat, suspended in water, and the statistical mechanics of those. Now, each of those each of those particles, globules, is different. Then they're completely not identical, sort of thing. And moreover, people have done experiments on them and actually measured a lot of the, measured the main quantities, and can directly compare the statistical mechanical calculations with experiment. And it turns out that you really do have to take into account the fact that if you have, say if you have four particles together, like they can even be little styrofoam balls that are just like in the solution, but in fact they're stuck together because of by a force called a depletion force. So even if they have no interaction between them, once you put them in solution, there is kind of an external pressure in some sense that forces them together, and that's an equilibrium configuration. So you can find them in an equilibrium solution. And the thing is that there are two basic shapes that they can make, and the symmetry number. I think you did symmetry number in condensed matter, right? The symmetry number of that has to be taken into account, because if you rotate it, if you permute the particles, then that's the same as one permutation rotated maybe 3 different ways, or some number of different ways, and so you'd be overcounting the states in the phase space. So that would lead to very large gaps in the accessible, well, not necessarily accessible region gaps. They are accessible, but you don't want to overcount them.
But isn't that regular?
Sorry?
Isn't that a regular?
Yes, it's regular, except that it's one of those. It's a combinatorial problem. It's the sort of problem that is done in the maths department, University of Western Australia, by Cheryl Prager and their group. Right. So there, I would be going to see what the mathematical theorems are about point groups and factorization of point groups and things like that, and see if I can find some regularity so I can calculate the number of accessible states correctly. Yeah. So you do need to take that into account. So it's not exactly the volume, again, not exactly the volume of the phase space, but something else. It's a measure on the volume, not necessarily what we would call the simple meaning of volume. Yeah. Okay, and as usual, I've introduced like the minimum for each lecture, and for today, the first part, which is just carrying on a little bit from last week, not the new material at all. It's the Microcanonical ensemble. I just want to carry on a little bit. Just the material from Reif is all you need to know. There's a little bit from Huang, and you don't need to do that. Part 2, you've really got to know all of it. It's really essential. The canonical partition function, try to understand everything on that. All right, so first of all, I want to complete something from that I started last week, and it's the sharpness of the probability distribution of the energy. In fact, I want to do it twice, 2 different ways. I really think that some of these ideas it's really useful seeing them derived from different points of view, because with each point of view you learn something, and it contrasts. You'll see, you will learn something from this one. So one of the things we showed, or we know, is that the equilibrium distribution of energy between any two subsystems in thermal contact only is determined by the equal temperature condition. And if you have an isolated system, you can actually divide it up into subsystems, and there must be, if the isolated system is to be in thermal equilibrium, then every pair of subsystems has to be in equilibrium. Any way you divide up the isolated system, they have to be in thermal equilibrium too. So that means that the temperature has to be even throughout. And just reminding you that the fundamental postulate of statistical mechanics, in equilibrium, an isolated system is equally likely to be found in any of its accessible states. Right. Now let's call the isolated system A superscript 0, A0, and it has 2 subsystems, A and A prime, and they're in thermal contact, so that the total energy equals E plus E prime. Now this E and this E prime, since the systems are in thermal contact only, they're in thermal contact, these are random numbers, because at any instant this can change, and if this increases, this one has to decrease by the same amount, by conservation of energy. Now the probability of finding the isolated system in a state where subsystem A has energy E, all right, is this P of E here. So this P of E we're looking at the isolated system, but it's the subsystem A has that energy, is some constant, is proportional to the number of accessible states of the isolated system when subsystem A has energy E. Okay. Now, since the sum of the probabilities has to equal 1, then that means that this constant times the sum of all the energies of this omega of the number of accessible states at energy E has to equal 1. So the constant is 1 over the sum of all the accessible states over all the energies. Now, this number of accessible states is by independence of the 2 subsystems. Now, we're also assuming that the subsystems are weakly interacting. They're so weakly interacting that they're not interfering with each other in any way. They're not preventing. One does not prevent accessible states from the other, or doesn't, like that. So they're independent. So that means that the total number of accessible states for the oscillator system is the product of the accessible states in system A and the number of accessible states in the rest, where the energy of the rest is given by that. Yeah.
Since aren't they actually linked with the conservation of energy?
Yeah.
For example, if the energy in one increases, then it should decrease it in another.
Right.
So the number of states accessible will be different.
But depending on the energy.
Sorry.
As in,
Yeah, what's the question?
the question is, since they're linked by conservation of energy,
Yeah.
wouldn't the number of accessible states also be linked? So they're not independent.
No. The fact that
The fact that one has a certain distribution doesn't prevent the other from having that certain distribution. It's the distribution that is independent,
yeah,
not the energy.
yeah.
But isn't the distribution also dependent on the total energy?
No, the distribution for an energy, for a certain energy.
Okay, and we know that the number of accessible states at energy E is a very rapidly increasing function of the energy. So omega B is volume in a more general sense than just ordinary volume of state space in a shell near E. It's a volume of state space enclosed between the origin and shell, but that's the energy per degree of freedom to the power of the number of degrees of freedom. And the reason for that is that if you have, this is of the order of, that means that it's a vast upper bound. So what we want to do is to make sure that you have taken into account all possible microstates of the system. So that one possible microstate is that, let's say this is this is momentum of particle n in the x direction. So if this, actually, what I should do is have the equivalent energy. So all the energy can be in here in the single particle in one direction. When the momentum is in a single direction, all the energy can be in here. That's the maximum. And no energy anywhere else in any other particle in any other direction. It's extremely unlikely, but it's something that we take into account.
It's an upper bound.
It's an upper bound. Yeah, sort of an upper bound. On the other hand, this dimension could be 0, this sort of dimension. And this dimension could have all the energy. So this is a degree of freedom. So this is, say, the degree of freedom the momentum of the nth particle in the x direction. And this is maybe the momentum, the degree of freedom, DOF, degree of freedom of the nth particle in the y direction, or the n plus 1th particle or something, anywhere, whatever. It's a degree of freedom. And so each axis, the upper bound is like E. E, all the energy could be in there, or all the energy could be in there, or all the energy could be in there, or any other dimension. The dimensions are degrees of freedom. Degrees of freedom. And there are F degrees of freedom. F, if you have n particles in three-dimensional space, then you have x, y, z for each particle. So that's 3n spatial degrees of freedom and 3n momentum degrees of freedom. Okay, so that's 6n altogether. So of course that's a huge number. So this is n particles in 3 dimensions. So that's E. So the volume,
So it's just E, not
it's basically e to the power of f. If I want to estimate the volume of that, it's of the order of e to the power of f, right? That's basically what I'm saying, e to the power of f. That's a huge number. But the thing is that it's e to the power of f. And f is proportional to n, the number of particles. So this is of the order of e to the n, or e to the 3n, or whatever. E to the f or e to the 3n.
So why is there the per degree of freedom?
Oh, I put per degree of freedom, I'm not sure, but that's what I really want to say there. And the reason I want to say it will become clear in a sec.
Professor?
Yeah, the number of degree of freedoms is just the q or q plus p. I mean the momentum.
It's every direction in some sense that you can pump energy into. So you can pump energy into the x direction of a particle's motion, or a y direction, or a z direction, or it can have in general, you could have some sort of interaction between them, and the interaction, say, a three-dimensional harmonic oscillator, and then you would be pumping energy into spatial directions as well as momentum directions.
So must be plus by the 3 n.
Yeah, 3, yeah. But what this is exactly doesn't matter. This is actually for I'm talking about an ideal gas here. The degrees of freedom. See, the thing is that a gas particle can have motion in the x direction and y direction and z direction. If I have a two-dimensional gas, say in the plane here, a two-dimensional gas, and because it's stuck between two plates, two very narrow plates, it's a two-dimensional motion, its heat capacity is two-dimensional, and say it's a classical gas in classical conditions. And if I take one of these surfaces away, that will become three-dimensional. That increases the number of degrees of freedom, even if I don't change the energy. And that's enough to increase the entropy because the molecules can't get back to a two-dimensional gas by themselves, unless I do that again. Yeah. So the main point is that the number of that omega of E very roughly goes as e to the power of the number of degrees of freedom. But that means it's an extremely rapidly increasing function of the energy. And we sensed this in the simple toy example in lecture 8. Okay? And this is the reason for it. But that means that now the number of degrees of freedom of the rest of the isolated system, because its energy is decreasing, it must be extremely rapidly decreasing function of E. E is the energy in the subsystem we're focusing on, right? And so you have omega of E is extremely rapidly increasing. Omega of the rest is extremely rapidly decreasing. The omega of the entire omega zero is the number of accessible states to the entire isolated system. That's the product, and the product is the envelope of those two. So that's going to have an extremely sharp maximum. Yeah. And so the probability of E is some constant C times this product. It has a very sharp peak, let's say at E tilde. And where is this peak, or what does that imply? Take the log of this and differentiate with respect to E and evaluate at the peak. Then that's the dln. Is that supposed to be? That's dln C. That's nothing. That's constant. dE by d by dE of log omega plus d by dE log omega prime. And because of the minus sign there, just use chain rule, that's a minus sign there. That's d by dE of ln omega, evaluated at E tilde, minus d by dE prime of ln omega prime, the E prime, evaluated at E tilde, and that has to equal 0. So that means these two different derivatives of the log of the number of accessible states of the two respective subsystems have to be equal, but that is a number that is we said that that's the entropy, and so that's the dimensionless entropy, the log omega. So that's the sigma by the E basically, which is 1 over kt, which is beta. Okay. So we want to understand, we want to just have a look at the neighborhood of the peak energy, around the peak energy E tilde, expand the log of omega of E in a Taylor series about E prime, let eta be E minus E prime, and so log of omega is log of omega E tilde, which is a constant, because this is just the value of energy at the maximum, times the linear term plus higher ordered terms in eta, and the terms, these terms should have an intuitive meaning for you by now. This one is the inverse temperature of 1 over kt, and this one here, which we'll call lambda, is in fact, since d by dE of log E is 1 over kt, basically then this is d minus d by dE of beta. That's that one there, that's the second order term. And so log of omega v is that plus beta eta minus half lambda beta squared. Can you put a lambda in there? There's a lambda missing. Alright. Correspondingly for the system A prime, the energy E prime minus the energy at the maximum, E tilde prime, is, well, that's E naught minus E, that's E naught minus E tilde, and that happens to be, well, E naught cancels out, and that happens to be minus eta, which is your expansion variable. So the log of omega prime is evaluated at its own variable, at its own energy, E prime, is this Taylor expansion here, where you've got a minus sign in there, and minus eta squared there. Like that. Then you add the two Taylor series, you get log of omega prime, and so you've got log of the constant, product of the constants there, plus beta minus beta prime eta, minus a half lambda plus lambda prime eta squared, and you omit higher terms because we're going to get in close to the maximum. And at the maximum, beta equals beta prime, so that linear term drops out. So you get the log of the probability of the energy is log of P of E tilde minus half lambda. Lambda naught is just the sum of the lambdas, eta squared. So the probability of the energy is a Gaussian with centered at E tilde. So that is the probability that the subsystem A of an isolated system has energy E. So this is a sharply peaked Gaussian. Do the omitted terms matter? When do they matter? At large numbers of degrees of freedom, omega is proportional to E to the F, so that the log of omega is about proportional to F log E. The derivative then is proportional to F divided by E. So lambda, which is minus the derivative of that, is basically proportional to F over E tilde squared, and so that's positive. And so the variance of the Gaussian is 1 over the sum of the lambdas, 1 over lambda naught. The standard deviation is 1 over square root of lambda naught, which is about 1 over square root of lambda. And so, and this is the standard deviation, not dimensionless entropy. E tilde, so that's the standard deviation of the energy distribution here is approximately E tilde over square root of the number of degrees of freedom. And so that's saying that, well, if the number of degrees of freedom is extremely large, like 10 to the 23, then that standard deviation is tiny. So yeah, for F is 10 to the 24, the relative width is 10 to the minus 12. This is an extremely sharp maximum. The other thing is that as the degrees of freedom tends toward infinity, then this relative width tends to 0, and the Gaussian turns into a delta function, and the mean equals the maximum. The energy equals the energy at the maximum, which equals the energy at the mean exactly, as long as you're away from the phase transition without fluctuations. Okay. Right. So the point here is that yes, the probability distribution of the energy of the isolated system turns into a Gaussian that's extremely sharp.
Professor?
Yep.
So is that a canonical ensemble?
No. This is microcanonical ensemble. Microcanonical ensemble. We talk about an isolated system and we split it into two. I should have made it really clear that the first part of this lecture is continuing from last week. Okay? We haven't said anything about microcanonical ensemble. To do that, about canonical ensemble, to do that I have to just define what a heat reservoir is. So what's a heat reservoir?
So first, this is not like a canonical ensemble because all the states have an equal probability.
Yes, all the states of the isolated system have an equal probability.
Yeah, as long as they're in the temperature, in
the energy range. Yeah. In fact, even if they're not, they're 0 probability. Okay, so we need to know what a heat reservoir is. So what if the other subsystem, the A prime, is huge compared to the first one? What does huge mean? Well, let's say it absorbs heat Q prime, which is a change in mean energy delta E bar prime. There's a prime there because it's to do with the rest of the subsystem. We've got the isolated system. We've got a small system. This is A prime, and there's A in there. So the dimensionless entropy, the change in dimensionless entropy when the large system absorbs heat Q prime is the log of the accessible states after it has absorbed heat Q prime minus the original number of accessible states. And Taylor expand the log of this one, omega prime, about the maximum in powers of the heat, because this is going to be a small quantity, relatively small quantity. So there's the linear term, and there's the second derivative term, and this linear term turns into, that's d log of omega prime dE prime, which is just beta prime, the inverse temperature, the inverse dimensionless temperature, 1 over kT times Q prime. And this one here is d beta by dE prime, Q prime squared. But what does it mean to be a heat reservoir? The heat reservoir, to be a heat reservoir means it's so big that the heat has such a large heat capacity that when you put whatever amount of heat, when your sample in the laboratory puts heat into it, its temperature doesn't change at all. So that's saying that d beta by d prime equals 0. This is basically the definition of a heat reservoir. D beta by d prime equals 0. And so all the and in fact, all the high terms then are 0. Okay, important point. All the high terms are 0 because all the high terms are just derivatives of that. This is identically 0. Identically 0. So all the high terms are 0. And so you just have this first term. So the change in dimensionless entropy is 1 over kt prime times q. In other words, q prime, delta S of the reservoir is q over t. Q prime over t prime, right? Which is what we already know from thermodynamics. But it's nice to see there's different formulas and get the same pattern. For quasi-static absorption of heat, ds equals dq on t for any system. Okay. I wonder if you can read the next section yourself. It's from Huang, section 6.2. It's just another way of showing that the energy is extremely sharply peaked. But the interesting thing about this one is the last point, that the dimensionless entropy of the two subsystems of the isolated system is additive, but it's not completely additive. It's approximately additive. We're talking about it's approximately additive. There's a term here that's about the size of log n. Yeah. And you can read that for yourself. I don't want to go through it now. I want to get to the point of the lecture, which is canonical ensemble. But this is interesting because it's this has been interpreted as an effect of the boundary of the interaction between the two subsystems at the boundary. I don't want to get into that, but I've read that somewhere. Okay. So anyway,
Is it like entropy of mixing term?
no, it's more like more like the energy of interaction, if there is one. All right, so I don't want to. So you can read this for yourself. This is just like a second derivation of exactly the same thing as we did before, but from a completely different viewpoint. Okay. Okay. So. So the canonical formalism and statistical mechanics in the Helmholtz representation. So the problem, you've probably already sensed the problem with the microcanonical ensemble approach. First of all, the combinatorial problem is usually too hard. Even in lecture 8, how much work we had to do for the trivial problem, not even a thermodynamic problem, with just one particle in 2 dimensions with an energy of, what was it, 48 units or 49 units. That's a huge problem. You know, it's a combinatorial problem that's NP hard, that one. Right. Or in general, it's too hard to find the shape of the accessible state surface, to find the boundary of the accessible region. If you can't find the boundary, how are you going to find the volume? Sometimes it's possible. It's something you should always keep in mind. And it's always a useful theoretical tool and for various arguments.
Why is it hard to find the shape of the surface?
Because what if what was this? You got these gaps.
Cool.
But the basic problem is that the energy is a fixed number. What if we could just have any energy? Well, then we would still need to count some kinds of gaps. Yeah, that's true. But at least we don't need to worry about the boundary of the accessible surface.
So why would we not have to?
Oh,
you have, energy.
because energy would then be from 0 to infinity.
Oh, okay. Okay, that makes sense.
Okay, so we just have energy from 0 to infinity, and you'd have a different distribution. So for this energy band, you'd have some distribution. For this energy band, you'd have some other distribution. For this energy band, you have some distribution, etc. But at least we don't have to worry about
Missing, like, the surface.
well, the surface. Yeah, you still have to worry about some types of gaps.
But wouldn't it be less important? Because we said that the volume is more concentrated in the outer region.
Yeah, possibly. Yeah.
So if there are gaps here,
Yeah.
and assuming that the number of states is equal, then there it would be more important.
Unless it's something like a quarter of the phase space. So if I had a molecule, say I'm talking about the classical approximation. If I had just say 2 dimensions. If I had a molecule of maybe sort of try to have 4 different, maybe 4 different molecules. Then if I try to count all the states of this, now this would also include rotations.
Yeah.
Here. Then if I rotate this like that, oops, minus cross like that. Let me see. Let me rotate it once more. So, okay, that's a rotation, but it's also a permutation. So if you were finding all the states by permuting, or finding all the permutations of this, and you are also integrating over the rotation variables, you're overcounting. You see that?
Yeah.
Yeah. So there's all sorts of subtle things like that. I don't want to get into that at all. I just want to do the basic theory. I'm just telling you that the actual number of states might be like a significant fraction.
So that's like
of
a
the
continuous irregularity. Like,
so it's some kind of regularity that can have quite a large volume of the phase space. Yeah. I don't want to get into that at all, but that's the sort of thing that can happen. But certainly, if you don't have to worry about where the surface is, that's certainly a big help. Okay, so the microcanonical ensemble says that for any accessible state of an isolated system, the probability is equal. It's either zero if it's not accessible, or constant, non-zero constant if it's accessible. So what you do is you remove the limitation on the amount of energy available for the system of interest. You consider all energies from 0 to infinity. Now, the energy, you need to also keep in mind that we're talking about completely general systems, not just ideal gas. So the energy, and we're also talking about, say, the semi-classical view. So we're talking about solving the Schrodinger equation, and let's just say we have some set of eigenfunctions, and the eigenvalues and eigenfunctions are many body eigenfunctions, many body eigenvalues. And the energy of the system would depend on things like, or the energy eigenfunctions would depend on the geometry of the container, interactions between the particles, and it comes from the energy ER. R is this particular state of the many-body system, a single state. That comes from solving the Schrodinger equation. Okay. Or for a classical system, the first integral of the motion. All right. Now the physical model that we're interested in is a system in contact with a heat reservoir. The isolated system has number of accessible states, omega total, E total, and each of those is equally probable. And E total is the energy of the small subsystem and energy of the rest, which is the reservoir. Because these are in thermal contact, in fact this energy ER fluctuates, in fact so does E res, fluctuates as thermal energy is exchanged. So if you had a device that's sensitive enough, you'd see get different values each time you measure it. E total is an arbitrary large fixed number. It's another thing. Alright, and so what we're going to find is the canonical ensemble for probabilities PR, in other words the probability distribution. So that's the ensemble, the distribution. For the subsystem, this one there. Subsystem only. Remember, Helmholtz representation focuses down only on the system of interest, and you don't have to worry about the rest. Don't have to worry about anything to do with the reservoir. So that's what we expect to happen here too. Okay, you can read that page for yourself about statistical independence. So the probability P sub R that the subsystem is in state R is the number of accessible states of the composite system, that's the entire isolated system, when the subsystem has energy E, but when the subsystem has energy E sub R. So that's a particular product of omegas divided by the number of accessible states of the isolated system. That's a sum over all products of omega for all possible energy distributions. That bit there you'll understand better after you read the page that I suggested you read by yourself. It's page 9 of 25. It's this type of picture. This type of picture here. There's omega of the isolated system. It's a sum of all possible products. You can read that for yourself, page 9 of 25. So for that, to understand what the difference between the numerator and denominator is, see page 9 out of 25 of these notes. Okay? Then that'll make it clear that the number here in the denominator is huge. I mean, that number in the numerator is huge, but this one's huger, hugely huger. Right? Now the number of that there is a product of omega of E and omega of the reservoir. But the omega of this number of accessible states of the system that we're interested in, and we are assuming that it is in state R. It's not in fact omega of R, omega of E. It's a number of accessible states. It is in state R, a single state. So that's 1. It is in a single state. That is why there's a 1 there. Right? But then that means that the reservoir has all the rest of, really defines the number of accessible states, omega res. And there's omega total in the denominator. So really what we've got is the number of accessible states of the reservoir when the energy of the subsystem we're interested in, the E sub R. So the energy of the reservoir is the rest of the energy. Okay. This is true, and so this is the probability of the that the subsystem is in a state R with energy ER. It's true but not useful. So we want a useful statement.
But Professor, state R is defined by all coordinates, as in like a state of...
Say quantum mechanically. So that means this ER would be a many-body eigenvalue. So in this section, I prefer to think of the quantum mechanical case, where we're not talking about phase space anymore. In quantum mechanics, you don't talk about phase space. So
But you're assuming no degeneracy.
Oh, it doesn't matter if there's degeneracy.
For
Doesn't matter.
We said one.
Yeah,
It's one state.
but there could be many with the same energy. Don't care. We don't care. Yeah. Right. It could be degenerate. It's fine if it's degenerate. In fact, it's almost certain that it's going to be hugely degenerate. Okay. So, now since S equals K ln omega, omega equals e to the S on K. But you know, omega has got something to do. This is counting the number of accessible states, omega, and it does have something to do with the space-based volume, accessible. It's not exactly the same, but it's got something to do with it, right? It's a measure. So the entropy here, e to the S on K, this thing here is related to a phase-space volume. Okay. Let U be the thermodynamic internal energy. Right, that's an average energy. So that's what that's the constant quantity that you measure if you measure the internal energy. Right. And the entropy is additive. It tells us that the entropy of the isolated system, the total entropy of the isolated system, equals the entropy of the subsystem we're interested in, plus the entropy of the reservoir.
And this entropy is additive comes from where? Which part?
That comes from the fact that the subsystems are statistically independent. That the subsystem and the reservoir are statistically independent.
Yeah, the axiom of probability multiplication.
Yeah. You know, it's true up to terms of log n. The instantaneous reservoir energy is E total minus E sub r, and it's always fluctuating about the equilibrium energy, E total minus U. So this here is a constant energy because it's an average, and this one here is bouncing around this one. So let's okay. So E res is E total minus ER. That's this one here. So that's a continuously fluctuating quantity. It's a random variable. And E res star, I would call it. This is the stationary average E total minus U. I just need some nice symbol for it. So E total minus U is just a macroscopic thermodynamic average there. Now, so E res minus E res star is U minus ER. Right. So now expand the reservoir entropy about the thermodynamic average energy. And note, remember that higher derivatives vanish because it's a reservoir. Right? That's a big, nice point. So now the reservoir at energy E res, which is a random variable, is reservoir at this is constant plus the first derivative of the reservoir entropy divided by the reservoir energy evaluated at the thermodynamic energy times the E res minus E res star, which is that, okay, because we're expanding about E res star. We're expanding this. This is a linear term. And all higher terms are zero because it's a reservoir. And so that's S res as a function of E total minus U plus, now this is 1 over the temperature here from thermodynamics times, and that is U minus ER there. Okay. Now, you put, let's see, you put that and that into there. So mix them up, put them all in the mixer. So what have we got? This here is e to the s res 1k, e to the dimensionless entropy of the reservoir, and in the denominator, e to the dimensionless entropy of the isolated system. That's that. But S1 on K S res is 1 on K S res is a function of U total minus U plus 1 on K T U minus ER. And in denominator, you got 1 over K S of U plus 1 over K S res of E total. So we've used additivity in the denominator, additivity of the entropy in the denominator. But, and you know, remember when we did the thermodynamics, all the variables, all the quantities to do with the reservoir cancelled out. And all you got was a focus on the system of interest. So look what's happening now. That's e to the that there in the denominator, e to the that in the numerator, that cancels out. Now all you're left with is e to the 1 on kt u minus er. This 1 over k, e to the 1 over kt u minus er. And here you've got e to the, taking that up to the numerator, e to the minus s of u on k, and we take out a t there, and you've got to multiply that by a t. So completely naturally, what comes out of the mathematics, what's that? That's the Helmholtz free energy. That's beta. We call that beta the dimensionless, inverse dimensionless temperature. E to the beta f. F is the thermodynamic Helmholtz free energy. And there you got e to the minus beta er. There. And that is the probability that the subsystem of interest is exactly in state R with energy E sub R. So we need to normalize the probability. So the sum of over all states of the small system. Now the small system might contain many particles, so it's a many-body system. Many-body system. So this R potentially has many. You need to specify a set of many things in here, many eigenvalues. So PR equals 1. So e to the beta f does not depend on R. So that comes out of the sum. So that sum equals 1. So that sum equals e to the minus beta f. Okay? So that sum is that sum is in fact the normalization that goes in fact that equals that in fact is a normalization, and that sum is given the symbol z, and that's called the canonical partition function. It's a function of tvn. Okay? And so we have that e to the minus beta f equals z. So z is a sum over states, individual states of the system of interest. It's called the Zustandssumme in German. That's why it's z. This equation gives you the connection with thermodynamics, the Helmholtz free energy. And this is a probability that the system of interest that's in contact with a heat reservoir only is exactly in state R with energy E sub R. That's called the Boltzmann probability distribution. So these are really maybe the most important equations of statistical mechanics.
Professor?
Yeah.
The canonical partition function is in the as the function of tvn due to the
Yes.
fact that like the transform or other reasons.
the T is in there, and the energy eigenvalue of the many-body system will depend on the volume. So you can think of the simple example of a particle in a box with perfectly reflecting boundary conditions. Imagine a single particle, and if you have a length, certain length, then the particle has a certain energy. If you halve the length, then that means you've pushed the wall in and you've done work on the particle, and it has higher energy. So the energy of the particle depends on the volume of the box that it's in. And if you have n particles, likewise. Yeah. And if you have more particles, then you have more energy.
Okay. Plus, you're assuming the discrete case, aren't you?
Yes.
With the eigenvalue of the
Yeah. If there weren't, then this would just be an integral. Yeah. Okay. So the expected value of the average energy. Now let's start. Now this is from the basic high school definition of average. Okay. So back to high school. The average of a quantity is the possible value times the probability of the value summed over all cases. Okay? That's just the definition of mean. Alright? So PR is the Boltzmann probability distribution. So it's e to the minus beta ER over Z. Z doesn't depend on R, so that comes out there. So the sum over R, ER, e to the minus beta ER. Okay, you look at that. What's your first thought? How will you proceed?
It's like if you differentiate to there's
Right. So you've got an e to the. So you've got an ER in the exponent there. If you differentiate with respect to beta and multiply by -1, that'll give you that. So you do that, and then you got sum over R, e to the minus beta ER. So you got -1 over Z, d by d beta, sum over R, e to the minus beta ER. But what's that?
Z.
Nearly. What we do, what's better, is to bring that inside. Oh, I see. You're going backwards. Yes. Yes, it's that. So I'm going backwards here. So go from here. So U is by definition that because we want to bring down an ER. But then take the d by d beta outside, and then but that's Z. So we've got 1 on Z, d by d beta of Z, which is just the derivative of a logarithm, d by d beta of log Z. So the internal energy is minus d by d beta of log Z. Okay, so that's another connection with thermodynamics. So basically, log Z, derivatives of log Z give you thermodynamic quantities. So if you can calculate log Z, if you can calculate Z, then you've got thermodynamics. The algorithm for calculating thermodynamic quantities is, okay, you are given a list of states. some list, doesn't matter. The quantum case is very simple, except if you have identical particles. It's very simple. List of states, and this could be a finite set or infinite set, and you're given the energy eigenvalues of each state. This is a many-body state, right? You're given the energy eigenvalues. You might have to solve Schrodinger's equation for it, or you might have to approximately solve Schrodinger's equation, or whatever. But you need the list of states with their energies.
But Professor, these states they can be further distinguished. We're just using energy derivation now. So we're saying that states are.
They don't care. So that just says that they're degenerate.
Yeah.
So sure, they can be degenerate. But what we need is the energy eigenvalues.
So the measure that we had, the probability of R, is just for the collective thing. So it's like the.
No, it's for a single state R. So it could be for momentum going to the right.
Or momentum going to the left.
No, just momentum to the right. And then another R would be momentum to the left. Separate, but they have equal probability. So they have the same energy.
Right.
Calculate the partition function. And so that means you try to sum the series if possible, or you probably won't be able to do that. So then the partition function gives you the free energy. Then apply thermodynamics. Okay. So the entropy and heat capacity. So these are two very important things that we should make sure we get. So if you do this time, we know that the internal energy is minus d beta of log z, but log z is minus beta f. So stick in thermodynamics already in the second line. But now f depends on t as well. This beta depends on t, and so there's beta, and f depends on t, so f depends on beta as well. So that's using product rule, gives you f plus beta df by d beta. So you need to find df by d beta, but df by d beta equals df by dt dt by d beta. Oh, okay, here it is. But dt by d beta, what's dt by d beta? There's beta equals 1 on kt. There's beta equals 1 on kt. d beta by dt is minus 1 on kt squared, which is minus k beta squared. So dt by d beta is minus 1 on k beta squared. This is worth remembering. So yeah, beta times that is just minus 1 on k beta. Oh, but that's just minus kt on k, which is minus t. So beta, zoom out. Beta dt by d beta is minus t. That's from there. Minus t. That's that. So we're left with df by dt. What's df by dt? S. Minus s. So it's f plus ts. So that u equals f plus ts. So what we've done is we've got a self-consistency check, but also we know that the entropy is minus dF by dt, which is k beta squared dF by d beta, sort of from up there. Now, let's get the entropy in terms of the log of the partition function. So, because we want to be able to calculate everything from the log of the partition function. So, minus beta f is log of z. Okay, so the f that we differentiate here is minus 1 on beta log of z. So again, you use product rule. So s on k, bring in the k on that side, it's got minus beta squared, so you've got d by d beta, that product rule. So that's minus 1 on beta squared log z plus 1 on beta d by d beta of log z. D by d beta of log z is 1 on z d by d beta of z, which is, so that's d by d beta of that sum. And that's sort of going backwards compared to what we were just doing. So that brings down a minus ER there. And that minus sign comes from that minus sign there. It's minus, so that gives you minus beta squared times 1 on beta is 1 on beta. And you got that after differentiating.
That's the average.
And that's the average of, that there is the definition of average of energy. So that's U, or E bar. So we could call it U. So E bar and U are the same thing.
Yeah, it's written down as U.
Oh, good. Okay. Yeah. So, so that means that if we have the partition function, we can calculate U and then entropy. Okay. Then the molar heat capacity is defined as T over N ds by dt at constant V, so the one at constant V. And so, what's the best way forward? It's most convenient to differentiate with respect to beta. So that's just ds by dt. Bring in the molar form of entropy. It's a tiny s, so make sure you don't make a mistake. So it's obvious. So it's okay. So T ds by dt multiply by k. So divide by k. Multiply and divide by k. So you get kt in the denominator. It's d by ds by dkt, which is the same as ds by. So that's 1 over beta. Ds by d1 over beta. That's exactly the same.
Yeah.
Right. But d1 over beta is so there's 1 over beta. D by d beta, 1 over beta is minus 1 over beta squared. So d1 over beta is minus 1 over beta squared d beta. So you replace d1 over beta there with minus 1 over beta squared d beta. So that means that goes in the numerator, minus beta squared on beta ds by d beta. So that's minus beta ds by d beta. Put back in and the entropy is log z plus beta u, and so
We just differentiate
yeah, so you differentiate
with respect to
with respect to beta. Differentiate that with respect to beta, dividing by n. Oh, this is actually exercise 16.1 from before. That's why I left out some steps, but this is trivial. Yeah. So anyway, so now you have the heat capacity. So the properties of matter are second derivatives of log z. So kappa T, CV, alpha, they're all second derivatives of log z. So you get log z, you get z, you got everything. And it also tells you where the phase transitions are. And that can be like number theory problems and complex analysis and stuff. Maybe I should just next week I'll just mention Yang and Lee theorem. Yang and Lee theorem. Yeah, these. I think Yang, C.N. Yang certainly won Nobel Prize. I'm not sure if Lee did. Maybe he did. But they're two Nobel Prize winners in high energy physics, but they were working in statistical mechanics as well, because statistical mechanics has a lot of mathematical problems. I mean, physical problems which are fertile for application of creative mathematics. So those sort of minds are really attracted to the field.
So, Professor, what is exactly a phase transition? Like, in terms of all of these?
Oh, hang on. It's a zeros of the partition function. Pole zeros. Yeah. You mean what is it physically, or what is it mathematically?
Like, how does it relate to all of these variables?
Oh boy, that's a question we answer in SP2.
Or what's the physically?
Well, okay. So discontinuity of specific heat, for example.
Oh.
So the specific heat would go, say, this is T, and it would go, this is CV, would have a different form on either side of some temperature. Okay. So this is for this is got a cusp. Whether this might be an infinity or it might just be like that. In fact, next semester we'll calculate for bosons. You'll calculate the specific heat for bosons and Bose-Einstein condensation. That I can't remember exactly how it goes. It's sort of sharp and then sort of a different form on this side, and that's discontinuity of the derivative. So as long as the specific heat is smooth, it's nothing interesting. Well, not in terms of phase transition, but if you have something like that coming out, and so that will be contained in the partition function. Yeah.
So it's only in the specific, or are there?
Oh no, there's there are other quantities like magnetization would suddenly change. So basically what happens in a phase transition is that the entire system, the entire many-body system changes its some property like magnetization. Suddenly, instead of having magnetic fields that are basically fairly randomly oriented, suddenly they're all oriented in pretty well the same direction. And so the magnetization suddenly changes.
So even the volume, I think, because we were doing an experiment in which the volume was changing because of some innovation.
Ice has the volume of ice would increase, that sort of thing. But there are first order and second order phase transitions as well. But what I described here is a second order phase transitions. This is so properties of the partition function tell you about phase transitions as well. It's one of those fascinating things. Anyway, the last point that I want to make for today is extremely important, and it's how the partition function factorizes into separate partition functions, each for a single mode of oscillation or single particle. It could be the same particle in different dimensions, or different, it just factorizes as long as the modes or whatever are independent. They don't affect each other statistically. So, for example, so what we're interested in is any way that energy can be given to a system and distributed among its excitation modes. So for example, molecules in an ideal gas or non-ideal gas, in other words, we're not specifically talking about ideal gas, it could be much more general, can be excited into higher rotational, vibrational or translational states. And the translational states don't, unless you're going relativistically, relativistic speeds, they don't affect the rotational states. And, or actually the translational states can affect, well, the vibrational states can affect the rotational states if the vibrations are large enough. If the vibrations are small, they're independent. Okay? So as long as these are independent, well, then you can put energy into them independently. This kind of, this putting energy into different degrees of freedom is the idea of what you really get. I think it's, I think that's something that some people in this controversy that I've been talking about are missing. Or people who believe in entropy as, they think it's just a statistical, not statistical, like a information theoretic interpretation. I think they're missing out on something important. In a strongly interacting system, such as a solid, and the opposite of an ideal gas, where you have interactions between everything. Right? The excitation modes, the normal modes of a crystal, for example, can be wave-like collective motions called, say, phonons. Well, actually, there are lots of different kinds of waves, collective motions. Phonons, sound waves, could be transverse phonons or longitudinal phonons. Magnetic spin waves, or spin waves, basically waves of the spin, the magnetic moment of atoms or whatever precesses like this, and you can make a wave propagate through the substance. That's another way that energy can be put into the system. And that can be independent of the translational, rotational, vibrational, etc. States of the atom that the magnetic moment is attached to. Okay. So this special case of weakly interacting systems, the particles are independent and non-interacting. So the ideal gas is a standard example. But more generally, excitation modes in a crystal, for example, normal modes are independent and non-interacting. Non-interacting means no energy is stored as potential energy. So an ideal gas means no energy is stored as potential energy between them. Relatively no energy, relatively. Independent means a molecule, etc., occupying one single particle state does not affect any probability that another molecule or whatever occupies its own state. Statistically independent. In this case, the partition function, which is a sum over R of e to the minus beta ER, where this R, and this is something that you've got to get your head around, and you will in the next 4 weeks. Okay? Hopefully within 4 weeks you'll get your head around this single step. Right? Is a label for the many-body eigenstates. Right? And R ranges over all possible states. R ranging over all possible states is equivalent to all individual particle states ranging over all possibilities independently. But remember, there are gaps. So there are some combinations of single particle states that might not be possible for whatever reason. Okay, so there are always these gaps. And the thing is that those gaps can happen in all sorts of places, in all sorts of regions in state space. Okay, so let R sub I denote the accessible states of a particle or excitation mode I, which has energy E sub R sub I. Okay, E sub R sub I. Right, so the partition function for the many-body system is by definition this, but If they are weakly interacting, then basically what we're saying is that we can find the energy eigenvalues of each of the particles or modes individually. This step here is a kind of a step from solving Schrödinger's equation. The wave function factorizes. Yeah, and you can find and Schrödinger's equation separates, if you like, into individual particle Schrödinger equations.
It's like separation of variables.
Yeah, separation of variables. Yeah. So and you can find all the energy eigenvalues individually, and because they are independent and the energies don't interfere in any way, or don't suppress each other in any way, or magnify each other in any way, these are simply added. There's a lot of physics going on from here to here. There's a lot going on.
So R ranges from all possible states for all of the particles.
Right, for the entire system, yes.
Yeah, and which means that every particle goes through its own states. All
Yes.
of them.
Yes.
And since they're independent, they don't affect each
Right.
other. So
Right.
we can write them as a summation of a summation of a summation.
Yes. Yes. And this here comes from separability of the Schrödinger equation. This is easiest to explain in quantum mechanically, or semi quantum mechanically, because we're not talking about we haven't properly symmetrized the wave function or anything like that, which is something we'll find out about in QM2 in first thing next year. In first thing after the break. Anyway, see, once you get to here, the rest is easy. The hard part is understanding going from there to there. Okay, once you get to here, then it's trivial, because you've got e to the power of a sum, so you've got basically just product of exponentials here, and each term in the product has got just a single eigenvalue, and all the eigenvalues are different, correspond to different particles eigenfunctions. Okay. And then you just, then put this exponential to do with particle 1 in this sum, rewrite the summation, but multiple sum, by the way, but simply like that, put that there, etc. And then each of these is just a partition function for a single mode. That would be a single particle, single excitation. So that means that the partition function for the many-body system is just a product of individual partition functions for single modes. Okay. So this is factorization of the partition function for weakly interacting subsystems. And these are completely general. They can be particles in a monatomic particles in a gas. Could be vibration, rotation, translation modes for ideal gas, diatomic gas molecules. Whatever. Okay. And so, since the Helmholtz energy, since log z is just basically the Helmholtz free energy times minus beta, that's telling you that the Helmholtz free energy is just additive over the molecules or over the individual excitations. Log z1 plus log z2, etc. So let's do a couple of quick calculations. So in a two-state model, where I think you did the assignment question, you see the Schottky hump in the specific heat. So each atom, so what's the prescription? You need the states and the energy of each state. Okay. So the ground state, so in a two-state system, you've either got the ground state or the excited state of energy epsilon, okay, 0 or epsilon. And assume that they're independent and non-interacting. So then if you have an n particle system, then the many body partition function factorizes into the product of the single particle partition functions. And what's the single particle partition function? It's sum over R1, say, e to the minus beta e R1, 1. But the two possible energies are 0 or epsilon. So that's either e to the 0, which is 1, or e to the minus beta epsilon, that's a single particle partition function. So that's just 1 plus e to the minus beta e all to the power of the number of particles. And so that's z, and now, and f is just minus 1 on beta log z. It's minus nkt of ln 1 plus e to the minus beta e. It's basically got it in 2 lines. Right? Whereas using the microcanonical ensemble, it took you half a page. Okay? And the other thing is that it's extremely simple to generalize the model. So for example, what if you have a 3-state system? You just have 0, E1, E2. So then instead of having just a sum of 2 terms to the power of n, you got a sum of 3 terms. Okay. And the free energy you can immediately write down as that. Okay. And once you have the free energy, then or you can work out the specific heat from the free energy or from log z. I mean, it's the same thing. Okay. You can either use thermodynamics, the thermodynamic route, or it turns out to be the same thing. Einstein model of a crystal. What about that? Each oscillator has possible energies 0 h bar omega naught, 2 h bar omega naught, 3 h bar omega naught. So the single particle or single mode partition function is 1 plus e to the minus beta h bar omega naught plus e to the minus 2 h bar omega naught plus etc.
It's 2 beta, right?
But that's 2, yeah, beta. There's a beta missing. Yeah. There's a beta missing. But that's just a geometric series. To get from one term to the next, you multiply by e to the minus beta h bar omega naught. So you can just sum that. That's just 1 over 1 minus e to the minus beta h bar omega naught. Like that. So you got that. So you immediately, so you know the single mode partition function. So the many body partition function is that to the power of 3n, because you have 3n modes in the 3n normal modes in the crystal. And so you write down the free energy. That's that. And that's like 3 lines. What used to take a lot longer. Okay. And then, of course, from this you work out the specific heat and whatever. Now the other thing, then the interpretation of the factorizability, if you're talking about individual molecules or individual phonons, each molecule or phonon can be considered to be in thermal contact with a heat reservoir consisting of the rest of the system. So the reservoir in that case is the rest of the system. And what this is saying is that statistical mechanics in the canonical formalism can be applied to single molecules. And right, whereas in thermodynamics, in contrast, applies only to a large number of macroscopic systems. So you can do statistical mechanics on single particles.
But then in many cases we assume that n is large.
As long as the particle does not interact with the particles around it, and it is in thermal equilibrium with it. So, for example, you've heard of Brownian motion, okay? So you can do this. You can do the statistics of a particle undergoing Brownian motion using statistical mechanics. It's a single particle in a heat reservoir of the air in this room. So that's an example in Reif at the end of chapter 6 or something, whatever it is. Okay, so there are plenty of questions to go on with. Yeah, a lot of these are just a few lines, but they're simple questions that give you practice. You know, you do these questions. Some of them are not so simple. I can't remember which ones are which, but they just give you practice in the new language. So that's it for today.